All right. Hello, everybody. Good afternoon. Thank you for joining us today. This is a CMTS Lunch and Learn with Argonne National Laboratory, talking about the development of American commercial shipbuilding analysis and strategy. So without further ado, because we've got lots of great information to talk about, I'm going to go ahead and pass it over to our colleague, Chris Kay.
Thank you, Michelle, and we very much appreciate the CMTS hosting us. And there's a lot of, as you can see, there's a lot of people from the Argonne side that have contributed to this work, and as well our collaborators from the University of Michigan, who we'll get to hear from as well during this presentation. With that, I'd like to actually hand it over to the Argonne Maritime Coordinator, Melton, who's on the call, and introduce you all to Argonne's effort in this space.
Hello, this is Melton Demirtas. I'm a department director at Argonne National Laboratory, as well as I'm a program lead for maritime R&D at Argonne. Argonne is one of U.S. Department of Energy's national laboratories, and there are 17 national laboratories under Department of Energy. We are located in one of Chicago's suburbs and established in 1946. This year, we are celebrating our 80th anniversary. Next slide, please. I'm pretty sure many co-authors of the 2024 Maritime Action Plan are likely on the call today, and we have also Argonne co-authors on this call. We have multi-agencies to develop action plan for maritime energy and emission innovation report. Especially, we provided characterization of the U.S. maritime sector in terms of vessel types, numbers, and energy consumption, and their operating profiles and the requirements. We also had to identify opportunities for technology advancements, as well as had the multi-agency co-authors to develop strategies in terms of understanding what will be the milestones, data gaps, as well as research needs. Next slide, please. So Argonne's overview of the maritime capabilities can be summarized in 8 different areas. One of them is marine energy supply chain risk assessment. We are really looking for viability of alternative fuels for the domestic and ocean-going marine sectors by conducting techno-economic analysis, as well as their technical feasibility, and looking for the bunkering risk assessments with an aim to provide supply chain security for the maritime industry in the United States. Argonne has a life cycle tool named GRID. We have over 65,000 users worldwide, 70% of those users located in North America. By using Argonne's life cycle tool, we will be able to analyze over 40 fuel types and 8 electricity production pathways for 70 different vessel types and sizes, with an aim to looking for their operating modes as well as their routes, with an aim to analyze the emissions for the application of these fuels for the different route types. We have another team is focusing on how we can design the vessels with the advanced propulsion technologies by integrating the electrifications. We are conducting again vessel cost analysis for the advanced component technologies incorporation. What will be the total cost of the ownership of this new vessel? So with the new advanced propulsion. Argonne also has a engine research test facility. In that facility, we have a 2-stroke engines that can allows us to do fuel testing. We recently test methanol and ethanol with an aim to understand how we can blend them to provide very low sulfur fuel oil by using those biofuels. We also look for the spray characteristics of these very low sulfur fuel oils as well as other biofuels that they have been tested at Argonne National Laboratory. Next slide, please. When it comes to the port operations, we are looking for system level analysis, and we are looking for also incorporation of the mode shifts across marine, road, and rail with an aim to decrease the transportation time for the commodity flows as well as transportation of the passengers along these three different mode shifts across the United States. We develop also marine footprint calculator with an aim to using the data provided by the EPA, and then we are including those data in our grid life cycle model to conduct the port inventory data analysis at equipment level, such as off-road, rail, or harbor operations. Our another team is focusing on shipbuilding and technology supply chains, as well as workforce development. We are really looking for shipyard throughput efficiency. We are looking for availability of material and components that they are needed for building new ships, especially ocean-going vessels in the United States. And we are also looking for supply chains starting from the steel or others to the final product delivery. We have been quantifying the capacity to scale production of assets. This is a very nice picture that's showing how we are integrating the material supply chain with the shipyard operations in the US. We have another tool, we call it Vision Marine. This is helping us to understand the fleet level energy and environmental impact by conducting their annual energy consumption for the entire US commercial as well as recreational vessel population. By using, again, Argonne's grid model, tank-to-wake or well-to-wake analysis, with an aim to project the future US commercial as well as recreational vessels for the entire United States. With that, I'm turning to Chris Coleggia.
Okay, great. Thank you very much, Meltem. So within all of this, we're going to dive deeper today into the specific U.S. shipbuilding vessel supply chain risk assessment work that we've been developing over the last year or so. And essentially, this is part of a broader framework to understand maritime risk assessments that includes the energy supply chain, which you can see on this little diagram on the bottom right, from raw resources to refinement to transport to ultimately making their way to the vessel, whether it's liquid or gaseous fuels, electricity, or even potentially nuclear fuel. The vessel supply chain, which you can see on the y-axis here of this figure, coming from raw materials, semi-fabricated materials and components, assembled into the vessel, using the vessel, and also incorporating the end of life of the vessel as well. And also, importantly, continuing to consider the vessel operations and the continuity of operations with regards to these different fuel or energy types and different vessel technologies or vessel type options in terms of maintenance or unplanned downtime, safety events, really driven from historically available data. And we, especially on the shipbuilding side, are employing a means of probabilistic risk assessment that we've developed at Argonne coming out of the nuclear and offshore gas and oil side of the lab to employ for supply chains, especially the shipbuilding and shipyard supply chain, incorporating a Bayesian network risk assessment. So as much with any kind of risk assessment, it's performed in 4 stages. First being risk identification, risk analysis, risk evaluation, and then sensitivity analysis. To date, we are in between the risk identification and risk analysis steps of the PRA for shipbuilding, supply chains, and shipbuilding. So that's today what we're going to be diving into and showing you all. So first, talking about the U.S. shipbuilding vessel supply chain. We looked at the Ships for America Act, and here's a list of the vessel types that have been identified as key to the U.S. Economic security and national security, as well as the different types of equipment that were identified in the Ships Act as key components for those different vessel types. The source of our data that we've been using up to this point has been a combination of the IMO's vessels registry, where we've looked at U.S. flag vessels greater than 10,000 gross tonnage delivered from 2013 to 2025. And then for those 76 ships that qualify under those constraints or those filters, we are pulling information from class societies such as ABS or DNV, the Bureau Veritas, or Lloyd's Register, to look at shipbuilding timelines, anywhere from steel cutting, keel laying, ship launch, and ship delivery. And within that, there's information for a given vessel where key components of the vessel are coming from in terms of their propulsion, power, cargo, mooring, steam, and other systems. And so that is information that you'll see where we've been tracking and trying to map with regards to at least these initial 76 U.S. flag ships that we've identified. So here's a breakdown of the 76 U.S. flagged commercial ships greater than 10,000 gross tonnage that were delivered between 2013 and 2025. The mean tonnage is 43,000 gross tons. And you can see based on the color coding, bulk carriers, container ships, heavy lift, miscellaneous, rows, tankers. And I'll mention that, the military Sea Lift Command and ships that are used for the Navy or for the military are included here. So, if you're looking at the question of where those heavy lift coming from, I'll point out that 41 of these 76 U.S. flag ships were actually built in the U.S. At peak, the U.S. built 8 ships in 2016, which were mostly tankers, you can see here. And that 33 of these 41 ships built in the U.S. were built in 2 shipyards. Thinking about shipyards and mapping them out, you can see 5 of the shipyards that were used to build these vessels between 2013 and 2025. The size of the dot is relative to the production of their shipyard capacity. You can see details here about dry dock capacity, numbers of ships that have been delivered in that time frame, total gross tonnage, and maximum gross tonnage that shipyard could output. So gathering the data from ABS on those ships that qualified that we're looking at, those 76, we can see that generally U.S. shipyards can take between 2 to 6 years to build ships, while other countries, so looking at the U.S. flag ships currently in the fleet that were built in other countries, we're looking at somewhere around 2.5 or 2 years or shorter time period for shipbuilding. And when we look at the different milestones, such as steel cutting to keel laying to launch to delivery, where we see the biggest discrepancy of U.S. shipyards compared to non-U.S. shipyards in this subset of vessels is particular in the fitting out stage from launch delivery. And so we think it'd be worthwhile to dive deeper into this milestone period to see what's causing some of these delays and where U.S. shipyard efficiency can be improved. So taking these 76 vessels, U.S. flagged vessels, again, over 10,000 gross ton delivered in this time frame, we can look at how the distribution of their delivery times, their total shipbuilding times, compares with that of the median across globally for global shipyards. And that we're looking at built in the U.S. about 68% take longer, whereas built, in a non-US shipyard would take roughly 16 to 19%, depending on the statistics you're using, longer than the median. And so this identifies that there's a significant need for improvement in vessel U.S. shipyard construction times, and that's a key area for us to think about. From the data, again, we only have a select set of vessels that we're evaluating, but one of the next steps in our approach is to start to drill down deeper into vessels of a certain type, as well as subsizes within certain vessel types. So here's an example looking at tankers and container ships built in U.S. shipyards compared to the median build time in across the globe, and we see that about 50% took longer in U.S. shipyards compared to the median globally, and that about 50% as well in container ships took longer. So as we continue to study and gain more data and more ships to look at statistically, we'll be able to evaluate other ship types and subsizes within those ship types to see what U.S. shipyards particularly can do well at, as where also we struggle at. So now, switching gears from shipyards to the material supply chain for those shipyards, I'm going to hand it over to Sarang Supakar from Argonne to walk us through a couple slides.
Thanks, Chris. Just a quick heads up that we tried to keep these couple of slides at a very high level to talk more about the capabilities rather than the specific application to a particular ship class or what have you. I'll just mention that some of these capabilities are being currently used on the defense side of things. So, they're up and running. I just want to give a high level overview of where they are. So the first thing that I want to introduce you to, maybe Chris, we can go to the second slide first, as a way of starting the story there. Perfect, thank you. So the first capability I want to talk about is what we call the arcade model. It's a dynamic material flow analysis model that uses Bayesian inference and some optimization techniques as its backbone. The key thing that I want to highlight here is the ability of this model to create uncertainty-aware material flows for a given material through an economy. So in the context of shipbuilding, if you think about steel, you saw steel on some of Chris's slides. So it's important to first understand how steel is consumed at a detailed level in our economy for a few different reasons. One, if we are looking to increase or expand the consumption of a particular grade of steel for shipbuilding, it is important to understand what other competing applications there might be in the economy that might get affected as a result. So this serves as a really good baselining effort for shipbuilding and related capacity analyses. The other thing that this model does is, if you look at some of the ways in which we might be able to track product lifetimes in some of these end-use applications like buildings, infrastructure, cars, for example, some of them are, they live on a decadal time scale, the others live on a shorter time scale. It does give us an indication of the amount of that material that flows back into the economy, right? So if we are to increase our production for a particular type of component or a particular type of vessel, it gives us, it sort of indicates ways in which we may be able to get some end-of-life material from other applications and repurpose it for expanded, shipbuilding capacity, for example. So just as an overview, rigorous Bayesian inference-driven methodology, it deals with data gaps and reconciles differing estimates from different sources really well. What it does is it'll give you the maximum a posteriori estimate for flows with credible intervals. So it acknowledges that some flows are and some estimates are more certain than others. So that once we have an idea of how a particular material flows through the economy, I guess the next question in the context of the discussion that Chris and Meltem sort of laid out is, what does an expansion to that infrastructure for producing some of those raw materials and intermediate products look like? So Chris, if we go to the previous slide now. That's where we want to introduce one of our modeling platforms, which is called Stream. Stream is it's an optimization-based industrial capacity expansion and technology road mapping model, which was developed at Argonne to assist DOE and other federal agencies with some high-fidelity industrial capacity planning. So at its core, it's a model that tells you which technologies to deploy, in what capacity to either expand or contract operations, where new facilities could be set up, and how and when to sort of add this new capacity or expanded capacity. So the phasing and path dependency is indigenously addressed in this model. The model is built to allow exhaustive sensitivity and scenario analysis, and we can look at economic, environmental, and operational constraints and objectives as well. We can also do multi-objective optimization and facilitate decision-making under uncertainties and sometimes under competing goals, where you are looking to balance the cost with the time to ramp up, for example, considering constraints around availability of energy resources and material and other infrastructure inputs and labor inputs. So the model was built to be very flexible. And so we can model something like steel just as well as we can model tortilla manufacturing, right? Not that tortilla manufacturing is terribly relevant for the naval applications, but just to sort of give you an illustration of how flexible the framework is. Now, going with this framework, very closely coupled is the ability to actually develop high fidelity representations of our existing production fleets. So in this case, if you look at how iron and steel is made in the US, on the previous chart, I showed you how the iron and steel sort of commodities flow through the economy, starting from raw material all the way to end products, right? But on a select subset of those nodes, we look at how steel is made in the US and how it's sort of imported in what quantities. So acknowledging that there are different technologies that can make steel, that they have requirements around raw material grades, that they have requirements around sort of after the steel is after the feedstock is prepared, the applications that it goes into, they might have their own constraints. So modeling or incorporating all of those, we develop a technological characterization, subject the existing fleet to an optimization framework where we minimize net present value of all costs, or we minimize the gap between supply and demand, and we subject the optimization problem to a range of environmental, economic, and operational constraints. And at the end, what we get is a spatially resolved, regionally resolved analysis of how and when and using what technologies this particular commodity can be made over what periods of time to meet the national demand for that given commodity over a certain analysis timeframe. So these two models are very closely coupled. They inform each other, and they represent sort of our industrial-based modeling capabilities at Argonne. So that's a very high-level overview. I'm happy to answer questions if there are any later on in the presentation. Thank you. Over to you, Chris.
Great. Thank you, Saran. So now let's switch back gears from the material supply chain, understanding steel and other materials needed for shipbuilding, to the components. So here you see a map based on those 76 vessels. Of the vessels from 2020 to 2024. So this is just a subset where we're able to have the time to dig deeper into the components that are on those vessels based on ABS and other class society registries. 12 of these 22 U.S. flagships were built in the U.S. 438 total components were documented in terms of their manufacturer location and what models and everything that they were. And basically if I can explain the legend here, the blue circles are shipyards, both in the US as well as in China, South Korea, Japan. We don't have any here in Europe because of these 22 US flagships, none of them were built in Europe. And the triangles, and let me back up and say that the size of the circle is also, again, relative to the size of the throughput or capacity of those shipyards. The orange triangles are locations of component manufacturers that are part of those 438 components that are on these 22 U.S. flag ships. So as we continue and expand to include more ships and more components, we'll have more detailed mapping, but at least this gives you an idea of the framework and the flow of different components, both within the US, such as engines, motors, generators, gears, and cranes, as well as for these 22 US flagships, the components that are being sourced from outside the US, including engines, motors, generators, propellers, anchors, anchor chains, cranes, elevators, boilers, and whether they're coming from from Asia and particular suppliers within Asia or in Europe. So looking at this fleet, and now this is expanding back to the larger fleet across 2013 to 2024, we see a distribution of the age of these vessels in terms of how old they are based on 4 different subcategories: bulk carriers, containers, ro-ros, and tanker ships. And the red is the median age globally of bulk carriers, containers, ro-ros, and tanker ships. And I'll point out real here, and I think some of you on the call will be really quick to point this out as well, that within the US, we have the Great Lakes bulk carrier fleet, which operates on fresh water and naturally has longer lifetimes because they're not exposed to salt water. And so within this distribution of 54 bulk carriers, or I'm sorry, that's the median of approximately, I think it's 150 bulk carriers, US flagged, that a quarter of those are the ones that are operating on the Great Lakes. And so pull those out and you still have a significant distribution of bulk carriers that are well beyond the median lifetime relative to the global fleet. The same can also be said for as bulk carriers as well as container ships. We see there's several container ships that are also older than the median, whereas the story is not as bad for ro-ros and tanker ships. Again, this is a subset, so as we continue, we're going to be adding to this and getting better statistics. So now looking into, for safety and efficiency purposes, vessels lose 80% value by age, by the age of 25. Fuel consumption increases by 30 to 40%, while maintenance increases by 80% as vessels get older than 25 years old. And based on a recent DNV report, most machinery failures, about 45% in 2024, occurred for vessels with an age higher than 25 years. And so that's why you see this analysis of how many of the vessels are older than 25 years old. Again, you can see in the US flagged fleet, we have quite a few vessels older than that mark. And so what we did here is look at data from this recent DNV report, which catalogs all of the different incidents, whether it's mechanical or fire or collisions, elisions, other sorts of incidents on vessels. And what they show is that there's a direct correlation between vessel age and an increase of incidents, especially in terms of mechanical failure, which can make sense. And so as the U.S. fleet ages, we don't only need to think about shipbuilding for new vessel types and key vessel types that we currently don't have, but we also need to keep in mind the needs to maintain and replenish the types of vessels that we currently have in the fleet, keeping in mind that as they age, their costs, their incidents, their mechanical failures are also going to increase. And so what we did here as a first step in looking at our risk assessment to build into our risk assessment is to look at the risk of machinery breakdown by vessel type, bulk carrier, tanker, container, and ro-ro ships, based on the age of the vessel. And as you can see, as the vessel gets older, moving from left to right, that there is a higher risk of machinery breakdown, and that there's a particularly higher risk of incidents with ro-ro ships based on this global data from DNV and UNCTAD. Then looking back internally at U.S. shipbuilding capacity by vessel type, you can see the number of ships that were produced from 2010 to 2023 in the U.S. We have, a certain number of tanker ships, container, bulk carriers, and ro-ros. And so the vessels that we are most at risk of needing to replenish would be those in the ro-ro and bulk carrier, where we need to increase our capacity for producing ro-ros 24x, bulk carriers 8x, while for the time being, we could reduce our need for container and tanker ships in the immediate future. So now switching from vessels to components, this is looking at those 348 components that were in 12 US built and flagged ships greater than 10,000 gross ton, based on data from the ABS registry. And you can see blue is showing the source from, that domestic source of that component. Orange is from a treaty partner, so one of our allies either in Europe, South Korea, or Japan. And gray would be from a non-treaty country where that component was sourced from. And this helps us to understand, of these 12 US flagged and built ships, what was the percentage of engines that were coming from the US, roughly 60%. So that's an area where we're doing somewhat well. And how much of the remaining engines were coming from our allies and from our non-treaty allies. And so you see that from an engine standpoint, 100% of those engines are coming from either ourselves or our allies. And we can kind of go down the list by different vessel components and identify what's the risk in future shipbuilding that we're able to sustain our shipbuilding activities domestically with domestically sourced components. And I'll just, there's some things that will catch your eye where there's no blue at all, such as anchors and motors and hardware, and ultimately where there's neither blue nor orange, such as boilers. So this is information that's going to feed into our shipbuilding risk assessment. And if we look closer, we can identify, within marine engines, certain size classes that the U.S. is especially strong at, such as, medium speed diesel engines. I'll just skip to this one here. Greater than 2,000 horsepower, we're especially strong at, whereas you won't see but much at all of U.S. built from slow-speed two-stroke diesel engines, whether less than or greater than 20,000 horsepower. We're sourcing those from outside of the U.S. Here, I won't go into details to save time, but we've been evaluating specific engine manufacturers and manufacturing locations. On the medium speed diesel side, in this RPM range, you can see Caterpillar is especially a strong manufacturer, which is a U.S. manufacturer. So with that, I'm going to hand it over to Erna Grelli, who's going to talk a little bit about the work we've been looking at into the hot topic of maritime and nuclear analysis.
Thanks, Chris, and hi, everybody. So nuclear is a little bit of a left field subject here, I think, in this overall presentation. But as Chris said, this is something that's been discussed very actively in the last couple of years. So we thought we would show off our proud history that's rooted in the research relevant to nuclear power. So as Melton mentioned in the very beginning, Argonne was established in 1946, and our primary mission was driven by that of the Manhattan Project. So on the left over here, you see a photograph commemorating a several-year anniversary of the first man-managed a nuclear chain reaction, fission reaction, was Dr. Enrico Fermi, and Dr. Walter Zinn is on the right, sort of unveiling the commemorative plaque at the site where the first nuclear reaction occurred at the University of Chicago. And then on the right, we see the picture of the USS Nautilus, which is the original SMR. So the original small modular reactor, which is a hot topic, was in fact marine, and it was run. It was the propulsion was enabled by the S2W reactor, which was manufactured and installed by the Westinghouse Electric Company, but it was based on its land prototype, the S1W reactor that was designed, built, and tested by Argonne National Laboratory. So that's a very important bit of history here. And later on, of course, the S2W reactor became a mass production template of success, which, you know, had a little bit different results in the military applications and the Navy applications than civilian applications. But this is essentially the research we're doing now, is trying to close the gap between the military success and trying to bring it over to you know, other commercial nuclear systems. So next slide, please. So one of the things that when it comes specifically to nuclear supply chain component risk assessment, and this is, I'm going to talk about a little bit of a framework that's been applicable and applied to the land-based reactors, but that can also be transferred to maritime. So the nuclear systems, really at the core, it's a system of systems. So thousands, maybe tens of thousands of discrete subsystems that present procurement items. And each one of those items is essentially carries its own risk. So whereas a lot of times we, in nuclear especially, we want to focus on the risk of cost overrun and how the overall cost overrun can be a function of cost volatility of the individual components and subsystems and subcomponents. The same sort of framework can also be applied to supply chain and availability. So when the system is broken down, leveraging a framework that was developed in collaboration with and based on the Electric Power Research Institute, EPRI, it's a code of account. It's a very elaborate spreadsheet. I do not have a screenshot of that here because that would not make sense. But it essentially systematically decomposes the nuclear power plant designs into their constituent subsystems to assess component level. So not only cost uncertainty, but also can be used for supply chain risk. So, and we feel that this, you know, this is a proven analytical tool. We've used it early in the procurement of the early test reactors that were built earlier on. And this is something that can be very applicable in the maritime shipping industry. So next slide, please. It'll just show you a little glimpse of what this EPRI Code of Accounts type framework looks like. And this is, again, a very high level snapshot. So what it does is it takes systems and subsystems and breaks them down into accounts. So account 2.0 or 20 is capitalized direct costs. So this is everything that goes into actually building the reactor, okay? So the 1.0, for example, would deal with its precursor, all the activities that would have to take place for the design, the pre-licensing, all of that sort of work, the permitting. Account 3.0 would deal with the operation and maintenance and the procurement of spare parts and things like that. And then there could be additional accounts depending on your application. So 2.0 capitalized direct costs for the nuclear system here would further break down into 2.1, 2.2, 2.3 as shown here. So for structures, for reactor systems, for turbine and generator, heat rejection, and others. And then structures, and this is where this framework, all the way on the left here, you could see it would need to be massaged and further applied to the civil maritime propulsion nuclear systems, where, you know, civil structures, buildings, all these things would apply less so, but what would you see more so would be, you know, parts relevant to the ship itself, ballast systems, excuse me, and other components that would ensure the stability and safety of the reactor. And then all the rest of the parts, like the reactor system, subparts like the reactor components and the reactor control room and many other branches down below would apply next. So for each one of those, the framework, the idea here is to do, you know, actual risk assessment of you know, the ability to procure each item. Okay, so the procurement is really at the core of the discussion here. That's all I've got, really. I just wanted to show you a glimpse of this widely used framework that we've applied. Back to you, Chris.
Thank you, Erna. Thank you for giving us a taste of the maritime nuclear nexus here. Another topic I want to touch on and introduce is a recent Argonne University of Michigan MOU that's been signed in the last couple of months. And the specific topic of maritime is one of our first areas of mutual collaboration. And so I'm going to invite Professor Matt Collette to come in and talk a little bit about work at Michigan and how it's fitting in with the work at Argonne.
Thank you, Chris. Let me make sure this is. Thank you, Chris. Can you hear me?
Yes.
Yeah,
Yep.
okay. So the University of Michigan is really excited to partner with Argonne National Lab. Michigan has a 145-year legacy of leadership in naval architecture and marine engineering. We were actually founded at a very similar time to the current time in 1879, where the United States had realized it had lost maritime competitiveness. After the Civil War, the U.S. had focused more on inward expansion, and we had fallen behind in iron shipbuilding and in steam propulsion to Europe at that time. And so we were founded underneath a congressional grant to start to build up those skills domestically. And since that time, we have been working on trying to promote the U.S. maritime industry. Unfortunately, we are currently the last remaining R1 or research intensive university that offers a bachelor's through PhD degree in naval architecture. We have some phenomenal collaborators in teaching. So, all the service academies and Webb Institute focus on teaching, and we have some small graduate programs scattered throughout the country. But at R1 universities, we are the last program left nationally. About 94 undergraduates, 81 graduate students, and 18 tenure track professors of practice. And as the nation has been trying to think about how to rebuild the maritime industry over the last 12 months, we have been making several major efforts to respond to this. The first is this MOU that we're talking about today with Argonne National Lab. We're really excited to kind of bring our knowledge of naval architecture to their work on supply chain and try to figure out how we should address rebuilding the commercial maritime industry. We've also started something called the Great Lakes Maritime Initiative that I'll touch on later, which looks more regionally at how the Great Lakes can contribute to our rebirth of maritime. And under the Navy's Nexus program, we've started the Bridge program, which is a graduate focus or a master's level focused program to train new naval engineers for NAVSEA and for the defense oriented community within the nation. And at the moment, we have 12 master students in the first cohort and are looking forward to welcoming another 12 to 15 this fall in the second cohort. So we're hoping to have almost 30 students underway by fall of 26 learning about naval engineering. The next slide, please, Chris. So one of the things that we brought or are bringing that we've developed internally that we're bringing to the MOU is this techno-economic model for how we can invest in rebuilding the U.S. commercial fleet. So we've built a model where we look at what are the supply chain possibilities that we have in the U.S., looking at first domestic production of ships, and then looking at the idea of what we could produce in allies such as Japan and Korea, what we could potentially purchase from allied nations as well that might be in their fleets today, and then potentially reflagging in ships that may have been built in competitor nations such as China as possible ways of building up a U.S. maritime fleet today. And we also look at what are the demands for the fleet. There's been a number of proposals out there. Ships for America Act has one list of possible vessel types. There have been some other policy white papers produced in DC proposing different fleet structures. And we look at kind of policy constraints as well as how much of this do you want to build domestically? What is your flexibility for working with allies for production, for reflagging? And what timeline do you want to have the vessels ready for? And we feed these into our techno-economic model, which is basically a large linear programming model that looks at your available resources. We pull data from US shipyards as well as using Clarkson's to understand the cost of reflagging in overseas productions. And we look at what are the possible strategies that you could do. So on the right-hand side is one of the outputs from the model that looks at what types of ships you would like to build per year to hit a certain target. This was a more aggressive strategy of trying to get a fleet ready by 2030 for a specific military scenario. And on the y-axis, you can see the number of ships we're trying to get into the U.S. fleet per year, color-coded by type. And then we also have similar results that show how many of these are being reflagged, how many of these are being purchased from shipyards overseas, and how many of them are being developed domestically. So with this model, we're really excited to kind of develop it further over the MOU. We're hoping to work with Argonne to show or to integrate all of that supply chain work that they showed earlier in this presentation. And this summer, we're hoping to host a joint workshop with Argonne on this techno-economic model and discussing what are the different policy alternatives the U.S. could pursue to try to rebuild our domestic ocean-going commercial fleet. And then with Chris, we have put in a proposal for a panel discussion at the SNAME annual meeting in Houston to also highlight what's coming out of this model. Next slide, please, Chris. The other two things that we're working on and hoping to expand our MOU partnership is the Great Lakes Maritime Initiative. So this is kind of a 5-pillar initiative we've just started this year at the University of Michigan. We're looking about how the Great Lakes as a whole, so Argonne, Michigan, other colleges within this region, other suppliers and shipyards in this region can help us rebuild our maritime industry. We're looking at 5 main pillars of activities. The first is the strategic maritime policy analysis. That's basically what we just showed off on the last slide, this idea of what are the techno-economic approaches that we could do to efficiently invest in our maritime fleet. We're also working on ship production and supply chain. So how can we improve the supply chain? How can we bring producers in the Midwest into the maritime supply chain and extend those that are already in the maritime sector? We're also investing in maritime technology development. So places where we think we could potentially leap ahead of our international competitors, such as digitalization, autonomy, AI, or maritime nuclear. We have some proposals out there right now. We're working on setting up a collaborative demonstration hub on the water in the Great Lakes region, so people, especially startups, can take new technologies and test them in maritime relevant environments at a lower cost than going by themselves. And we have several related activities going on in education, looking at everything from the skilled trade workers all the way up through continuing professional development of already established engineers. And one of the first things that came out of our Great Lakes Maritime Initiative was a proposed Southeast Michigan Maritime Prosperity Zone. So one of the things that the government has talked about doing is establishing these maritime prosperity zones. So we've tried to set up one for the Southeast Michigan, working with maritime industrial-based suppliers, innovative companies like New Lab, which is a startup incubator, as well as Lyft, which is one of the manufacturing centers set up under President Obama, as well as our port authorities and other research institutions. Next slide, please, Chris. The last thing I will mention is that we are also looking at trying to extend our work in maritime nuclear under this MOU with Argonne. So we are looking at different possible applications of nuclear to maritime, all the way from floating power and data centers to producing renewable fuels or working on direct ship propulsion applications. And we have a number of students already researching this in combination with the nuclear department at the University of Michigan, trying to figure out all of the potential interactions between the reactor and the ship, all of the regulations that will need to be changed, and what sort of investments we're going to need if we're going to really bring nuclear back into the commercial maritime world. And under the MOU, we've kind of started to work with Argonne with our internally funded project that has kicked off in the last year. And then we have submitted a couple of joint proposals already with staff from Argonne National Lab to further develop maritime nuclear. And Chris, that's it from me. So back to you. Thank you.
Thank you, Matt. I'm just going to pull up the tail end here to give a quick summary. Essentially, Argonne and the University of Michigan have significant expertise experience and expertise, as you've seen, in maritime energy and vessel research and analysis to assist the U.S. government and private sector to develop a commercial shipbuilding strategy. We're gathering background data to identify key supply chain risks of materials, components, shipyards, and putting all this data and knowledge together to build and employ quantitative models that can evaluate different shipbuilding scenarios and help to as I mentioned, help the U.S. government to come up with an overall shipbuilding strategy. So with that, very much would like to thank Michelle and CMTS for this opportunity to talk about this work that we've been carrying out. To this point, mostly internally funded. So if anyone on the call has ideas of RFPs that are out or will be coming out, please let us know, as we'd like to continue to expand this work without external funding and continue to solidify our partnership with the University of Michigan here. So with that, Michelle, back to you if there's time for any questions or comments.
Yeah, Chris, thank you so much for you and your colleagues at Argonne and Michigan University for joining us today. I foresee many questions, if not today, in the future, and many conversations to be had as your work and the work of our members continues. I'm going to go ahead and quickly stop the recording.